Alright, good morning, good afternoon, good evening, class. This is Mr. Arosena, and today in chemistry we're going to talk about how to use the KSP equation to predict product formation. So if you remember from last day, we talked about KSP in a little bit more detail as just basically a specialized case of KEQ pertaining strictly to solubility equations or solution equations, more specifically how things dissolve and whatnot. So today, we're going to use the KSP to determine whether precipitates actually get created or not. And actually, this is actually kind of, you saw this in the lab we did, I think last week, where I had you guys filter out the copper precipitate, but then at some point you were unable to make a precipitate, and we'll explain why. All right. So precipitate formation, I never mentioned this in previous chemistry classes, but precipitates will only form in one condition. That's if there are sufficient ions to reach equilibrium. Okay? So basically what this means in terms of KSP is that the cation concentration and the anion concentration must be equal to or greater than KSP. Okay. If the cation anion concentration is less than KSP, then there's not enough ions to make a precipitate. So in the lab we did last week where you guys had to filter the precipitate and then dry it out and had you guys do a second filtration. The second filtration, most of you guys didn't actually get any precipitate in the second formation, and that's because there were just not enough ions of either the carbonate or the copper to get to KSP, which would allow the precipitate to actually form. So if you're given a problem and you're asked to determine will a precipitate actually form, we have to define a trial ion product, which we'll call Q. So this is similar to, if you remember from the last unit, where we defined a trial KEQ, which we also called Q. And then depending on what value that Q had, it determined whether the equilibrium shifted towards the product or whether the equilibrium shifted towards the reactants. In this case, we're going to use the trial ion product, which is basically the same thing as the trial KEQ. And we're going to use it to figure out whether the precipitate will form or not. Okay. You can this will come in, I guess there are like three situations that will happen with regards to Q. And you guys can probably already guess what they are. So our three cases are as follows. I kind of already mentioned them. The first case is that if Q is less than KSP, that should be less than KSP, not that. That should be strictly less than. So less than KSP. If Q is less than KSP, then no precipitate will form, because as I mentioned, there are not enough ions in the solution to cause the equilibrium to shift to the solid side. So things stay in solution. No precipitate gets formed. If Q is equivalent to KSP, in this case, there is just enough of each ion present to cause a minimum amount of precipitation to form. Minimum amount of the solid to form. Okay. This is like it would look cloudy, but still somewhat clear. You wouldn't see like huge chunks of it in the solution. If your trial ion product Q is greater than KSP, again, it should be greater than KSP. Okay, let's see if we can clean it up a bit. So if this is greater than KSP, okay, so I'll just cross this out. We don't need that. So greater than KSP. So if Q is greater than KSP, then a precipitate will definitely form, and this would manifest itself as it would look really solid, really cloudy, similar to what you guys saw in the lab last week, where as soon as you added the carbonate to the copper chloride, a bunch of solid cloudy material appeared. That's this situation here. That's this situation here. Okay. After the filtration and you start filtering things out and no more precipitate happened, that would be this situation where your Q is less than KSP. Okay. Right. So that's how we can use KSP to predict whether a precipitate will form or not. Okay. Now this is kind of useful because in the realm of, I guess, like we were talking about last week with industrial chemists and wanting to clean things up, if your Q ends up being less than KSP, then that means that the ion concentration is too low to cause a precipitate to form. That's generally safe then. That's generally safe. Okay. It just means that that there's so little of it that it doesn't matter. Okay. All right, so let's go through some examples of how we can put this into practice. All right, so here we have a solution of silver ions and chloride ions, and we mix them together. There's the equation for the equilibrium. There's the KSP for the silver chloride. Let's calculate the diluted concentrations. Then we can calculate Q, and then we can compare that to KSP and see whether a precipitate will form or not. All right. Okay, so the dilution concentrations, we'll calculate that first. So let's move this stuff down here for now. All right, so dilution concentrations will be as follows. So we need to know what are the concentrations of Ag plus, and this we can take the original volume. Now, here's something that will be very useful for everybody. Actually, I shouldn't do it this way. All right, here we go. This is what I'll do. I'm going to calculate the moles of Ag first. Okay. And you'll notice that in previous mole calculations, I always converted the milliliters to liters, but if you do the following, so we want to multiply this by the concentration times 10 to the negative 5 molar. Okay. If you leave it in milliliters, so if you leave it in milliliters, then the resulting answer, I believe this will be 3.0 times 10 to the negative 4, I think. Just confirm that. So 5 times 6 e negative 5. Yeah, 3 times 10 to the negative 4. Okay. Now, since I left it in milliliters, this is not going to be in moles. This is going to be in millimoles. Okay. Now, the reason I bring this up is because if you work in millimoles, you don't have to convert your milliliters to liters, so you can skip the conversion steps, right? So if you work in millimoles, you can leave everything in milliliters, which is great, because that's one less conversion you have to do. So now that you've got the millimoles of silver ions, you can then take the concentration as the number of millimoles, 10 to the negative 4. Oops, I messed that up. 10 to the negative 4 millimoles, and then you can divide this by the milliliters, the total milliliters, which is 15. 15 milliliters. The milli part cancels out, and we get 3 e negative 4 divided by 15. So we get the concentration of 2 times 10 to the negative 5. So 2.0 times 10 to the negative 5. Yeah. Now, this does, again, make it a little easier, because when you do the concentration for chlorine ions, well, for chlorine ions, we can then do the same thing. We can do the 10 milliliters times its concentration of 4.2 times 10 to the negative 6, and then we can divide this by the 15 milliliters, and this will give us the number of, or the molarity of chlorine. So let's do that. So 10 times 4.2 e to the negative 6 divided by 15, so at 2.8 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the negative 6 molarity. All right, so there's my diluted concentrations when we mix these two solutions together. All right, now the next part is to calculate Q. So Q is the product of silver ion concentration times chloride ion concentration. So this will be 2.0 times 10 to the negative 5 times 2.8 times 10 to the negative 6, which will be, this will be 5.6 times 10 to the negative 11. All right, and then we compare that to KSP. Let's grab the KSP from up here. So there's, oops, grabbed a little bit too much, that's okay. There's our KSP. So we compare it then. So how is 5.6 times 10 to the negative 11 compared to the KSP value? Well, 5.6 times 10 to the negative 11 is smaller than 1.8 times 10 to the negative 10. So therefore, no precipitate is created because we do not have enough chloride ions, nor do we have enough silver ions to create a precipitate. So the silver ions and the chlorine ions just kind of stay in solution. Okay. There we go. All right, that's kind of how we can use KSP and the calculations to help us figure out whether a precipitate gets formed or not. Okay. Now another type of problem that you would encounter with this is, let's suppose, this is another one. Okay, so let's suppose here we have another solution of lead nitrate mixed with magnesium iodide. We want to calculate Q and compare it to KSP. So here we have two solutions, lead nitrate, magnesium iodide. We mix them together and we'll see if a precipitate gets formed or not. With this example, what you want to do first is figure out, will there actually be a low soluble compound? So ask yourself, like, is there going to be a low soluble compound? Okay. Because if there's not, then obviously there'll be no precipitate. So the lead nitrate and magnesium iodide, as we know, everything with a nitrate is always soluble. So that means that magnesium nitrate is obviously not going to be it, and we already know lead nitrate is not going to be it because lead nitrate already dissolves. So the only other option then is we check if PbI2 is soluble. Okay, that's the only other option we have. And why is that the only other option we have? Well, if you think back to Science 10, where we talked about double replacement reactions, this is a double replacement reaction. Okay, and remember we sort of augmented this double replacement reaction in Chem 12 by saying that other stuff happens because, as we know, this nitrate compound is really not an actual compound, but it's just going to be a collection of ions like that. Okay, now this lead iodide, we'll check the lead iodide, and that should be a low soluble compound. Lead 2 plus for the most part is generally low soluble in just about everything, except for nitrate and some other things. There you go. So there you go. So this is going to be the precipitate that we expect to form. Okay, provided we have enough lead and iodine ions. So how do we go about figuring that out? Well, the concentration of lead ions we can pull from this information here. Okay, whoops. We can pull from here. Oh, these are supposed to be concentrations, so that should be molar. So we'll pull from there. Okay. Now this means then that we have to write a couple of other equations. Okay. What do I mean by that? Well, the lead ions, I'll pull it from here, come from the lead nitrate, which means that lead nitrate will dissolve into the following. So one one lead nitrate will produce one lead ion. Which is great, because then we can just pull this. We can say this. 4.5 times 10 to the negative 3. That's the concentration. We're going to dilute it, so we'll multiply this by the 25 milliliters. And we'll divide that all by the total of them, which will be 60 milliliters. Okay. So we've taken the concentration of the lead nitrate. That concentration will give me the concentration of lead ions. And then we can do our dilution calculation like we did for the previous example to get the diluted concentration of lead, which is going to be 4.5 e to the negative 3 times 25 divided by 60. So we get a total of 0.001875, so 0.001875 molar. All right. Now we'll take our magnesium iodide. I'm going to write down the equation for magnesium iodide here. It dissolves into 1 part magnesium and 2 parts iodine. So whatever this concentration is, we'll get twice as much. So this is 2.8 times 10 to the negative 3. That means this will be 5.6 times 10 to the negative 3 because we have twice as much iodine ions. All right, so the diluted concentration of iodine will then be 5.6 times 10 to the negative 3 times 35 milliliters divided by 60 milliliters, and we get the following. All right, so 5.6 e negative 3 times 35 divided by 60. So we get 0.00327, 0.00327 molar. There you go. Now you have our concentrations. All right, so we have our concentration of lead ions, we have our concentration of iodide ions. All we need now is the KSP of lead iodide. So we'll look that up. KSP of lead iodide is... Alright, so according to my table, the KSP of lead iodide is 8.5 times 10 to the negative 9. Alright, so let's see. Our Q will then be 0.001875 molar times 0.00327 molar. And this is going to be calculator 0.001875 times 0.00327. So we have a total KSP of, let's see, 6.1 times 1, 2, 3, 4, 5, 6. So 6.1 times 10 to the negative 6. That's my Q. And this is obviously bigger than 8.5 times 10 to the negative 9. So we can say then that a precipitate is created. Okay. And most lead compounds have very, very low, most lead compounds have very low solubilities, or very low KSPs. So they get created, lead precipitates get created quite often. Okay. All right. On to the next example. All right. So here's one where it's kind of the flip side, where we're given a condition we want to make a precipitate. We have a solution of chlorine ions is added to a solution of silver ions. There's the KSP of silver chloride. And we want to figure out what is the concentration of chlorine needed in order to create a precipitate. And this type of question is a little easier than the other ones, because all you have to do is say, okay, we know that the Q has to equal KSP in order for a precipitate, in order to precipitate. Okay, it has to be at least greater than or equal to. Okay, so that's easy then. So we set up our equation as follows. 1.8 times 10 to the negative 10 equals, if I have a solution of 3.6 times 10 to the negative 3 for my silver ions, then multiply it by the solution of chloride ions, and that'll be, then I just rearrange this algebraically, and that'll tell me how much I need how much chlorine I need in order to precipitate the silver out. So we'll divide both sides by 3.6 times 10 to the negative 3. So this will allow me then, Cl minus will be 1.8 divided by 3.6 is 0.5 times 10, so negative 10 plus, or negative 10 minus negative 3, so negative 7. So in proper scientific notation, 5.0 times 10 to the negative 8 will be the amount of chlorine that we need. Okay, anything more than that, and we'll definitely, so this is minimum amount. Oh, geez, minimum amount needed to precipitate. There you go. So that's one use of KSP, just figuring out when precipitates happen or how to make a precipitate happen. If if I wanted to extend last week's lab, I could have extended to just how much carbonate do I need to add to your filtered solution to precipitate the rest of the copper out. Because the carbonate solution I had, I think, was 1 molar, and we kind of had no idea what concentration the copper solution was, but you guys worked it out. Good, so there you go. So that's what we can use KSP for. Anyways, your assignment is as follows. Have at it.